Okay. So where are we? So to higher value causes overfitting, causes accurate prediction on training data but inaccurate on test data. Underfitting is inaccurate for both data and test because the algorithm is kind of like either is too weak or just very small for the data set. It's not complex enough, or the parameter tuning is not kind of optimized. So it could be at least those two reasons. I'm not sure if I can think of the other reasons. So if that happens, um, so the algorithm, because the algorithm is kind of weak for some reason, either because it's small, is a just like small literally means like a very simple algorithm because let's say it only has two parameters or three parameters, right? Or the parameter itself is not optimized. So if you put tons of data, uh, for example, you want to predict the cause of cancer and has, for example, has a million of parameters, but you only can put three parameters. Of course, then it's not going to be accurate, right? Because it's too simplistic. So in that sense, it's not going to be accurate for both the training and the test, right? Um, I think the so in that sense, you want to have a more overfitting problem than underfitting problem, I think, because if it's overfit, it kind of means, well, it also means your mathematical function is too big or too complex because the data is kind of too small, or the hyperparameter, the way we tune it, is too precise, right? So yeah. Um, okay. So typical values range from 100 to 1000. Okay, for the number of so I kind of like this then actually. Hmm. 100 to 1000. Hmm. That's like the number of algorithm. But in deep learning, how do you do this in deep learning? In deep learning, I'm kind of off tangent here, but because I learned about deep learning quite a bit, so I'm just trying to um, decide the thing about how do you use this? When do you use deep learning? When you use XGBoost with the right parameters, right? Because it's kind of in a way there's kind of similarities there. In deep learning, you have just one kind of um, neural network, which is kind of a very flexible algorithm, and it's depending on how many features or columns, right? Because the features in the columns that you put, do you want to put you want to include, or how many like if you want and if you think it's necessary to do feature engineering, then the neural network is kind of keep on like growing organically, kind of depending on the input, right? Um, or is it not? Is it can you choose also the number of nodes? Yeah. Because you can choose the number. You can choose in neural network. You can choose the how many layers. Okay, how deep is the layer? So this is going to get more complex basically, because basically for each layer it's kind of like uh, add you add one additional layer. It's kind of like a decision tree added. So in a sense, you add more like algorithm. Okay, so interesting. So okay, now I see why like XGBoost is kind of like the performance is kind of like very good, just like probably as good as deep learning or just slightly worse than deep learning, or even in some data is kind of better than deep learning because okay, now I see that. It's interesting. So here is the code to set the number of models in the ensemble. So So you say my model equals to XGB aggressor and an estimator of 500, and then after that you fit it with X train and Y train, right? Um, and then you can do early stopping rounds, offers a way automatically to find the ideal value for the N estimator. So it doesn't have to be 500. So this one is like iterating, like adding, like first just one by one algorithm, and then two algorithm, three algorithm, four algorithm, and just keep on recomputing that and see if the error keep on going down. And then this, so I think this is kind of the maximum value that you put. And then there's a early stopping round, so it can stop automatically to find the ideal value. So if it's like, I think uh, the error doesn't keep on going down, it goes up again, then it will stop. So early stopping causes the model to stop iterating when the validation score stops improving. So there you go. Even if we aren't at the hard stop for, I don't know what is that. It's smart to set a high value, okay, and then use early stopping rounds to find the optimal value time to stop it. Okay, got it. Since random chance sometimes causes a single round where validation scores don't improve, hmm, you need to specify a number of for how many rounds of straight iteration to allow before stopping. Okay. Setting early stopping round is 5 because it's a reasonable choice. In this case, we stop after 5 straight rounds of iterating validation scores. Okay. When using early stopping rounds, you also need to set aside some data for calculating the validation scores. This is done by setting evaluation. Wait, okay. When using early stopping rounds, you also need to set aside some data for calculating the validation scores. Hmm. Okay, so this is like the validation data that you split into two. Okay, we can modify the example above to include early stopping. So you put the same thing here, and then during the fitting, you put early stopping 5, which means after 5 rounds, if it keep on deteriorating the validation, and it will stop. And then you use a separate if validation set data, right? The X valid and Y valid. Okay, so because you need to stop. Hmm. Why do you need to put that early stopping rounds? Oh, oh, because you're using different validation data. Got it. Because you want to know when to stop, right? So you need to use data to do that, right? Um, but if you don't want to know when to stop, you just keep on using the maximum number of algorithm, which is in this case is 500. Then you keep on just reiterating um, or fitting the algorithm. Like once you assemble it, one, two, three, you just keep on recomputing it, right? But if you want to know, because then it's going to be wasted if you keep on adding the number of algorithm, but it's going to be overfitting or um, it's underfitting. So you want to know, then you need to get the validation data. So okay, got it. Okay, this makes sense. Yeah, 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 yeah. Because this is like computing the mean absolute error in automatically, right? So remember the previous session when we compute mean absolute error by hand. I mean, just instead of automating it. So first you train the algorithm, right? You fit it with the train data set and Y data set. After you train it, um, you want to validate, right? And then so you use the validation data, and then you get the the prediction, and then you compare that prediction. That's when you use the mean absolute error. See how big is their error. Okay, so this is the same thing. Yeah, it's just being done like internally. Okay, verbose is false. I don't know why is that. Um, if you later want to fit a model with all of your data, set an estimator to whatever value you found to be optimal when run with early stopping. To fit a model, when you later want to fit a model with all of your data, set n to whatever value you want to be optimal when run. Okay, okay, okay. So the learning rate. This is really like um, deep learning actually. Yeah. Instead of getting predictions by simply adding up the prediction from each component model, we can multiply the prediction from each model by a small number, known as learning rate, before adding them in. So getting so instead of getting predictions, so you get the predictions after you train the data, um, and then you use that algorithm. You put the validation data set, and then you get the Y prediction, right? So instead of just simply adding it up from each of the algorithm, each component model, we can use multiply the prediction from each model by a small number. So you get the prediction, but you multiply by some small number. This is called learning rate before adding them in. Okay. This means each tree we add to the ensemble help us less. So we can set a higher value for an estimator without overfitting. If we use early stopping, the appropriate number of trees will be determined automatically. In general, a small learning rate and large number of estimator will yield more accurate XGBoost. Okay, this means each tree we add to the ensemble help us less. Ah, okay. So learning rates. Because in learning rate, the way I remember it in deep learning is for how big do you want to jump? Yeah, like how big the error should be, kind of. So we can set a higher value for an estimator without overfitting. So it's like you can put more algorithm. Okay, because the learning rate is kind of small. Okay, because if you use a learning rate, big learning rate, yeah, okay, yeah. Anyway, okay, I think I got it. Yeah, it's kind of the same as the deep learning, I think, the concept. In general, a small learning rate and a large number of estimator will yield more accurate XGBoost model. It's the same thing as in deep learning. You have to use smaller learning rate. It's better because if you use big learning rate, there's a chance that you overshoot. Overshoot means your error, instead of getting smaller, it keep on getting bigger, right? So you would rather like take a small steps going down the hill rather than take a big steps, because if you take, because sometimes the graph is like this, like curvy, like a letter U. Imagine letter U, so it's going down, going down. If you use like a learning rate like big, on the way going up is fine, but on the way down like this, it could be like from here it goes to there, and that's already like on the way up, right? So you want just like small step, tuk, 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 until at the bottom, and then you will see, right? But if you take a big step, which is a big learning rate, you boot, and then boot, and then goes on the opposite side of the curve. Um, okay, so as a default, you put 0.1. Modifying the example above to change the learning rate, you'll see the following code. So you put XGB regressor, you put the number of algorithm maximum is 1000, learning rate is 0.005, and then you put the fit X train, Y train, early stopping around 5. So you stop it after 5 rounds of deterioration, and then you use X valid and Y valid validation to determine whether you will have to stop or not. And jobs. Okay, another parameters here. On large data set where runtime is consideration, you can use parallelism to build your model faster. It's common to set the parameter n jobs equal to the number of cores on your machine. On smaller data set, this won't help. It's common to set the parameter n jobs equal to the number of cores on your machine. On smaller data, this one parallel to build your model faster. Okay. So this is just a way to make it faster. Because let's say if you're running because it's a parallel processing. So if you, for example, if you have running on a laptop or a desktop using, let's say, 6 cores, which means there's 6 chips. So you want to put the n jobs equals to 6, right? So it's going to be like faster because each of the chips can be utilized at the same time, running at the same time. The resulting model won't be any better, so micro optimizing for fitting time is typically nothing but a distraction. Okay, but it's useful in large data set. Okay, yeah, of course, where you would otherwise spend a long time waiting during the fit command. Got it. So here's the modified example. Okay, so you put it under the when you're defining the model. So you define the maximum number of algorithm 1000. You define the learning rate, um, and then the number of parallel jobs you can do for. Okay. Conclusion. XGBoost is the leading software library for working with standard tabular data. Okay, it's for standard tabular data. Okay. The type of data you store in pandas data frame. Got it. As opposed to more exotic types data like images and videos. With careful parameter tuning, you can train highly accurate model. Okay. All right. So let's go to the exercise. I'm gonna see if this one works already. Okay. So next session is gonna be exercise for XG boosting. All right. Thanks for listening. Bye.